Welcome to Graph Databases. I'm Clint Mitchell, and I'm here as the room host. And so we're glad to have Michelle. Thank you very much, and we're looking forward to your presentation.
Thank you. Today I'm going to talk about Neo4j and how awesome it is. Actually, graph databases in PHP. Neo4j is one I use, but there are several. They all work with the same principle, so we get the same principle from learning some about Neo4j. I have stage fright, so if I'm shaking, I'll try not to drop the mic. But ignore it. I'll do my best anyway. So, as Code Rabbi said, learn the most by sharing your knowledge with others. So, whee! Here I am! This talk is entry level, so if you know a lot about graph databases, or you played around with Neo4j, you'll probably not learn that much. But you can stay for this cute picture. Or a picture of me with a dragon. So, I'm Michelle Sanver. I'm a co-president of PHP Women, which is an awesome user group. We support people in PHP. If you're wondering about my accents, I'm actually from Sweden. I'm half Danish. I lived in the Netherlands for 6 years. And since about 2 years back, I live in Switzerland. And I work for this awesome company called Leap. I'm not sure if you heard about it, but it's amazing. We work a lot in Symfony, and my everyday job is writing APIs. So I'm a backend developer. So I obviously don't work for new technologies, and this is an awesome hobby that I have. So I got into Neo4j a few years ago, and it was my sister's now husband. He was running a Neo4j user group in Stockholm, and he told me how awesome it is. And I had this project in mind. Maybe I can use graph databases for it. So I started playing around, and I fell in love. It's amazing. So let's look at graphs. Yay! So graph theory has been studied since Leonard Euler's preaches in 1736. That's a really long time. And it started with him having a problem. He tried to calculate the best way to cross all of these bridges once only, and finding a theory for how he would do this. And if you abstract all these bridges into something you call a graph, you get something like this. You have 4 islands and 7 bridges. And this is the graph theory. If you abstract it, it will be a lot easier. So, what are graphs? They're really just connected data. They are everywhere, literally. There's graphs in this room. People have connections to each other. Here's some companies you may have heard of that uses graphs. Adobe, T-Mobile, Cisco, eBay, and lots more nowadays. It's modern. And some of you may use Facebook. They have the Open Graph, which is awesome, and it really connects all the data that they have. So a graph is really just an easy way to visualize connected data. So Michelle likes graphs. So a relational question might be, what's the average age? And let's calculate the data on this list. Let's enter a lot of data, and we only have tables and lists. And you might start asking more complex questions, and mostly from third parties. How am I somehow connected to this company or this country or this person? How many people, how many nodes is it between us? To find out those answers in a relational database, you have to make really, really complex queries. But in a graph database, you can traverse it, and you will easily find your answer, which I really like. So, relational databases have tables. For instance, this recipes table. They obviously have relationships, which causes a join table. So I query via the table, and imagine if that's all gone, so you actually see what you have. You have two groups and you have spaghetti, and they're both connected to it. I think that with modern data, it's a bit easier to read. So relational databases have a structure that you have to follow. But Neo4j has no schema. You can throw in any nodes that you want, which can be both a curse and a blessing, but it's really, really cool. Let's look at the EAB model, which was introduced in a relational database to try to actually have a relational database, but with no schema, to have it flexible. Then one single query, suddenly, because you want all the flexibility, looks like this, and it doesn't fit almost like, yeah. This is from a popular PHP framework. Yeah, so having a flexible schema database costs a lot. So if you want something flexible, you need a database without a schema. So for modern complex data, would you still really pick a relational structure? So let's look at Neo4j. The website is neo4j.org, and Neo Technology, which is a Swedish company, yay, is behind it. It's Java-based, and it's open source, so we can all contribute to it. There's meetups everywhere, literally. Everywhere around the globe, you can find a meetup. You can learn more, and you can have a lot of fun. So, graphs have nodes, which can be a person, item, or anything you want to represent. And nodes, they can have properties, as many as you want, and as many relationships as you want. Importantly, they can also have labels, so that you know that this node is a person, this node is a room, this node is a recipe. And indexes for easy lookup, which makes it a lot faster. So here's some common name graphs. There's the local McLaughlin graph, which looks kind of beautiful. And there's a diamond, butterfly, Wagner graphs. And you can see that in graphs, you often find a pattern, and the pattern can tell you a lot about your data and what kind of data you have. You can make art out of your database just by playing with data. Don't. You want to kind of zoom in and look at the structure from a zoomed-in state, not from a zoomed-out state. Even though it can be pretty beautiful. So, I started using Neo4j in a project called OmnumHub, which is like GitHub but for recipes. So you can fork a recipe, which is kind of a pun. And you can see all your forks. You can join groups, search similar recipes. And honestly, it's just a pet project, and I got almost nowhere. I talk more about it than I write it. But it's amazing, and the technology behind it is really, really cool. What you can do with graph databases in a recipe website is much more amazing than what I could do with relational databases. I'll show you why. But let's first dig into Neo4j architecture. So, like any database, or at least disk-based databases, you have the disks in the bottom, and preferably you almost never hit the disk, because you want to hit the cache system. And above that you have all the APIs. The core API, the traversal API, and the Sanver. Sanver is the query language, so it's kind of like SQL. If this is tricky, just ask me questions at any time. I really don't mind. So let's start looking at traversals. They define what to traverse. So you can go depth first or breadth first. And you can only visit once. And then you need to evaluate, and the graph needs to decide, am I done here, or should I continue to traverse? And that's what you specify in queries. How deep do you really want to go? And then, in a graph database, what costs the most time is to find the starting nodes. Where do I start in this graph? From where do I traverse? And from here, it begins. So, Sanver, as I said, is SQL for graph databases. And I think that's what makes Neo4j a bit unique compared to other graph databases. There's a lot of different languages to try to query a graph database. And some try to have more SQL-like language so that developers today are used to it, but they don't really match a graph. It becomes really, really tricky to make complex queries. Well, in Sanver, it's actually pretty easy. So parentheses means nodes, or like Igor Wittler says, hugs. Curly braces means properties. Square brackets means relationships. And that's all there is to it. They make it really easy to visualize and query the data. And so let's look at the browser. Let's run Sanver. Live demo. Alright. Let's see. If anyone doesn't see anything, or if it's too small, let me know and I'll submit. Let's first delete all the data. Don't do this in production. Okay, I already did that. So here, we're creating one user. Let's implement it. So just like in any query language, you use keywords. Create is a keyword. Return is a keyword. You can say marked in blue. And user is our label. So we want to define that we're a user node. And we want a property on the node, and we name it Michelle. And then we return the node because otherwise we won't see the beautiful graph. So here we see on the screen, we actually have a node. Yay, a first node. But it's not really a graph yet because that's all there is, one node. So here you can also see as a table if you want, and return it as rows. And what I think is really, really cool, which I recently added to the browser, is that you can see what kind of queries that you do. And I'll show you more about that later. But what fun is a database with only one user? Let's make another one. And now we have Xmas. So let's make us friends with our relationship. Here you can see that you match me, which is a user, with the name Michelle, with friend, which is a user with the name Xmas. Me and friend are actually just aliases, so you can name it to whatever you want. It's like variables in PHP. You define them so that you can use them later. Define them here, use them here. And as I said, parenthesis means nodes. So you can easily see match this node with this curly braces, which means property, with this other node with these curly braces, which means property. And then you create a node with these square brackets, which means relationship, with this other node. Note that you define which direction the relationship goes. So here I'm a friend of Xmas, but he's not necessarily a friend of me. But when you query the database, you can define if you want to query with direction or ignore which direction it goes. So you can choose to use directions, or you can choose to just ignore them. And here, because we didn't return anything, you can see only the rows. Created one relationship. Done. So let's create a user who is not my friend, but a friend of Xmas, to start having some more interesting data. Here we see more keywords, match, and we see the parentheses again, which is a node. And now I'm using another syntax so that you get to see both syntaxes. So you can use user.name, which just means the property, Xmas. I tend to use curly braces to try to stay consistent, but if you see these queries, you know what they mean. And then we create a friend, which is a user label, with the name stranger. And we immediately connect the friend to Xmas. And now that we have some users, let's match our users. And again, n is just whatever we call them, let's call them users. And it's a good idea to set a limit, because if you have a big data set, you can get into trouble here, especially in the browser. So here you can see the connections that we actually have. Michelle is a friend of Xmas. Xmas is a friend of stranger, and stranger and me is not connected, which is a really, really nice way to visualize a graph really, really easily in the browser. Questions so far? No? Okay, cool. So let's make a recipe. Again, we have the parentheses and the curly braces. And then we return a node so we can see the recipe. There we go, spaghetti bolognese. Easily created. So let's now add a relation to this recipe, because I made it. We also see in this browser that we have a warning triangle up in the corner. That's not really so good. It's a feature that Neo4j recently added, so that you can see potential things that you're doing in your query that may or may not be the best idea. So here, it's saying that this query builds a Cartesian product between disconnected patterns. And it's a warning that it gives us. So we might want to reformat the query, or in this case, I know it's a simple query, so it's not going to be so problematic, but we might want to use an optional match if we have a really, really big query where it might not match. Here we know it matches, but if we know it might not match. And the browser really helps here. So here we see Michelle and Spaghetti Bolognese. And we have this created relationship with the timestamp that we see down here. And Neo4j also gives everything an ID. So as you see here, this is ID 7. Every relationship, every node, everything has an ID. You cannot impact this ID. So never, ever, ever, ever depend on ID. Because then you will run into trouble. I had that. Also, it is quite difficult to get unique nodes. So if you want a node that is Michelle, and another node can't be named Michelle, then the best way to do it is programmatically. So let's create another recipe with a relation to my friend. So here again we match user, where username is VeraHaxmas, and we create a recipe with title Spaghetti Puttanesca, which is an awesome spaghetti family. You should try it. Ta-da! So let's get all of my friends. Oh, I only have one. Let's return friends and me to see how it looks like. So let's get the friends of VeraHaxmas. So here you see Stranger, Michelle, and VeraHaxmas. And as I mentioned earlier, if you query on a label or something specific, you can speed it up a lot with indexes. So here we want an index on the user label, especially on the property name, because we make a lot of queries on name, so it's a really, really good idea. And it's really, really simple. Create index on username. Done. So now we're actually getting somewhere. Let's try to make some more complex queries. Because now we have a data set which we can use. So again, parentheses means nodes. Curly braces means properties. So here we want to match a node which we choose to call me, but we can call it anything, which has the property name Michelle. And we want to match the relationship friend of. And here you see this asterisk 2.2. So that means we want to traverse the graph to a depth of 2. And then the node on the other side is friend of friend. And then we want to see friend of friend who has the relationship created, and then the node on the other side is a recipe. So we want all the recipes that my friends created. And it is also important in this case to add a not case. So we don't add me, where we have a friend of friend relationship. So if we return friend of friend recipe and me, we will get all the recipes of my friends and friends. So all strangers recipes. Or no. Let's see. Live demos. Did we forget this one? We probably forgot to make spaghetti pesto, so let's make it again. Yeah. So here we can see that we have stranger, which created spaghetti pesto, but I'm just in no way related to this. There's no lines, there's no nothing. And in this way you can traverse the graph, you can go as deep as you want. And because of the way graph databases are set up, your starting node will be me, and then you go from there. And when you found the starting node, it's incredibly quick to go anywhere, which is really cool. So the way you query this in PHP or in most programming languages is actually via their REST interface. You can also go directly, which has some performance increases, but the absolute easiest way is to go via REST. And it's really easy to use. So here we see Michelle has ID 7. So let's just have a look at what we get if we get DB data node 7. So here you can see all that you can do with the data. If you call this outgoing relationships, get relationships, you can get the labels, properties, incoming relationships, or anything. You can see the metadata, labels, and the data itself, which is all your properties. And then, of course, you can go deeper and get the properties. And what's really nice is that these queries are also actually just made in the REST interface, but the browser is doing it for us. And that's what I briefly showed you before. So it's actually doing behind the scenes, we can see here. It posts DB data transactions, and then it commits. And the payload that it has is this statement that we have. And that's really cool. And it comes back with the results, which is in Neo4j JSON, which I'm sure you're all familiar with. And then you can parse it from there in your application and do whatever you want. Really cool. And of course you can do a lot more in Sanver. You can do basically anything you want.
So what is the tool that you're displaying all of this on the editor or wherever?
Okay, I'll show you. This is the browser. So when you install Neo4j on your computer, you get the browser included. The default port is 7474. So if you go there, you get all of this. And actually in the beginning, if we clear all of this, it will look like this. So that's how you really start learning Neo4j and how you start playing around. So here you can jump directly into the code, get walkthroughs, monitor the system, or learn about Neo4j. If you're curious about this after you left, just press start learning after you installed it. And then here you can go through right in the browser. And you can start writing queries as you learn about. It's really cool. So here you see what a graph database is, all the things I just explained, relationships, properties, and then you can go to Sanver, start learning about the query language, and then you can actually run these queries directly in here. So it's really nice and useful tool, and it comes by default when you install it. So it's just to use it, and this is the way I recommend anyone to start playing around with Neo4j and just use it, have fun, see your data, and see what happens. Any other questions? No? Cool. Yeah.
So do you know if this is a good fit for in human descent, descendancy charts or ancestry charts and stuff like that?
Oh yeah, it's definitely really, really good with ancestry charts because you have all the relationships between all the people and you can find one person and then go however deep you want to go. So
Probably the best way how you can store relationships between people.
definitely. I'll go a bit deeper into use cases after the demo, and I'll show how I used it in some other projects. And it's really, really nice.
Are there ways to make, you talk about labels, so maybe a person with a label. If I wanted to make, say their name required if I create labels, is that kind of thing easy to do? Or?
Yeah, programmatically. You can't do it in a query because, as I explained earlier, Neo4j is a schema-less database.
Right.
So you have no schema, you have no requirements, you have no really...
So you have to maintain that programmatically.
Yeah.
The database isn't going to...
Yeah, that's a bit of a drawback if you need that specific requirement and your data to look in a very specific way. You either have to do it programmatically or you have to look at other solutions.
So if I'm creating, like, if I'm just sitting there creating people like you're doing, I could just add whatever properties I want on these people, and it's just add them. So if I type all wrong, so you have to be really careful with this.
Oh yeah, you have to be really careful because otherwise you have properties with weird names. But then you can make an update query and update all the wrong properties.
So programmatically, are there, maybe you're going to get to this, but if I'm trying to connect to this in PHP or whatever, Java, or I guess, are there libraries that...
I'll get to it. Okay, so now back to the architecture. So the Neo4j architecture in the file storage is NeoStore. So NeoStore has several different store files. Each store has specific data. So for instance, the nodes, there are always 9 bytes. And every node is a single file. And 1 byte is used for the in-use key, and the rest is for the node itself. Fixed size means it's blazingly fast. And relationships have 33 bytes, which is in a different file. And then you have all the properties, indexes, strings, arrays, and then DB. Now, graph databases are key value storage. So there's no things like storing specific dates or integers or things you may be used to from other databases. It's key value. And like any other database, hardware matters. It really, really matters. So imagine caching in memory or file system, the performance impact it has. If you run out of memory, it starts caching on disk. And that really, really decreases your performance. So make sure you can have as much as possible in memory, because then it will serve your data fast. So more memory, and more memory. So now let's go to Neo4j in PHP. As we saw, there's a REST interface that we can use with any REST client that we're used to, any framework or anything. I like using Symfony with it. There's Neo4j for PHP, which is a PHP wrapper for the database. There is nothing like Doctrine or OGM of any kind. It is currently in discussion, and probably we're going to write it within 2016. We'll see how that goes. So here you can, in this Neo4j in PHP, require a client and then do anything you want with it. Anything. So here's an example how you can make the node in the client. So here I'm making a recipe node. Set property, spaghetti bolognese, description, Italian words, ingredients a lot. And then I save it. Then I can get the ID and do anything I want with the ID. Which is really, really cool and really easy. And if you use the Sanver, you want to make really, really complex queries. You can't do complex matches, for instance, inside of Neo4j client. So you really, really want to use some Sanver queries from time to time. But it supports it, so that's cool. It's really, really well documented, so you can start playing around with it. And of course, there's a bundle for that if you're using Symfony. Neo4j client bundle is really cool. So let's look how I saw on the map the future of it. What you can do in graph databases is easily find out what different users might like. So let's see. You both really like carrots, you might want to be friends. And you can see these have similar ingredients, similar user base, so they are probably similar recipes, so we can try to group them. We can add things like you might like. We can have smart recipe collections. And Neo4j makes it really, really easy to be creepy and know more about your users and all the connections that you have, which for modern databases and modern websites is all you want. It's about being creepy. As freaky as it is, it's true. So, graphs are everywhere, literally. To make it easy to connect data, easier to creepy. On a hub called Epic, and it's open source. And the docs for Neo4j are really, 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 really nice. You can play around in browser, as you saw there's an intro and a start, and you can do a lot of it. I also highly recommend Ian Robinson's book on graph databases. Neo Technology gives you the ebook version for free. And to get started, you can go to neo4j.org/learn. Thank you. Questions?
What? Using this for a tree structure, it's fairly good. What would be the process to do that?
So what kind of tree structure? Like
Yeah, just like a tree structure where, one thing is related to everything else, but through other relationships, and finding out which descendant, which.
Okay, so a tree structure is basically just a graph. So it's really easy to put it in a graph database. And then let's say this example with ancestors, you have me, and then you have my direct family. And you can go, okay, what were 5 steps up? So you traverse the graph 5 relationships in the past. And then you can find different structures. And then all the connected nodes to that. And traverse the structure and where you want, which makes it an item in this case, I would say.
You mentioned something about the IDs before that don't rely on those. Is that what you
No, the IDs, you have them. The internal structure relies on IDs.
said? Oh,
But if there's a lot of IDs, maybe you delete the queries, the IDs can be reused. So the ID is never really something you can rely on. So don't rely on an ID, but try to query again if you need any of the data.
Are the properties and labels, are they case sensitive? Or is it, like, if someone types name or uppercase versus name, would you treat them the same? Or would
Good question, I don't know, let's find out. Okay, let's, okay, so here we have the name property. So if we do this, yeah, they're case sensitive.
what would be some, I mean, we talked about kind of the family tree, that's a good use of it. What are some ways that you've seen companies using this over, say, a traditional relational database where it excels?
Okay, so when I was a freelancer, I got this really creepy client. It was a health insurance company from the UK. I don't want to mention which one. And they wanted to find out, okay, so if a person has these symptoms, they had these diseases in the past, should we increase how much they should pay based on how likely it is for them to get more horrible diseases? And then you can make relationships between all of the diseases and all of the symptoms and see how likely it is for you to die next year. So that's a use case, a really creepy one. But there's other things, for instance, like flight data, which is really nice. So you can connect flights with destinations, and you can see what plane flies where really easily and connect them. And obviously social graphs is one of the major use cases. And music, movies, those kind of things. But you can use it for any modern data that's connected.
So we sell computer systems in our company, and what we looked into is to basically build a structure of all the components in that specific system, and then you can even connect it to customers, so you can see which components have been sold to which customers through all the systems. So there's a lot of possibilities there.
Yeah.
You said that the fields are all the same size. So what? I mean, what is the what would be the impact on a graph database versus like a more traditional relational database, as far as space used on the hard drive? I mean, you talk about that you need a lot of memory, but I'm thinking about hard drive space. Is it going to be significantly larger, or what's been your experience on that?
I never really experienced it being much larger, but it's also because hard drive space is cheap, so I never run into any issues with it. I think hard drive space is usually nowadays not an issue. You can have a really large database and you still don't get up to 500 megabytes yet. So it's...
As kind of I guess it's sort of a follow-up. What about scaling? Like, do you find that it's easier to scale a graph database than a relational, or?
I personally find that it's harder, but it's because I don't have so much experience with it. But with, for instance, MySQL, you can really easily scale with masters and slaves and have 1 million servers.
Right.
And in graph databases, you can also add more servers to it and it scales. But I would suggest to go to a hosting company or to, for instance, Graph Story, and they can host your graph database for you and help you with all the scaling when it comes to that.
you mentioned with the data types, it's basically strings, I think that you said you're storing. So are there functions if I wanted to figure out how old someone is or that sort of thing? Is there functions for casting?
There are
calculations?
there are a few, so you can do min, max, and some other common functions in the database. It's not so commonly used, but there are some that you can use.
Okay.
For instance, one thing that's really cool is that you can count the number of relationships and the number of nodes. So if you have a graph and you want to see how many relationships it is, you can just use count and then see, okay, there's 5 relationships to this node, and maybe that's all you want to know. Or you can see the minimum number of something. Any more questions?
So on the homepage, you have mentioned like eBay and Walmart are using it. Like in what fashion are the commercial websites or commercial applications using this database?
I only know exactly how some of them are using it. The companies that I showed varies from Neo Technologies website. So I don't know exactly how all of them are using it. But I know in our retail marketing, for instance, we're doing that. We're matching, if you bought bananas, you might want to buy apples, or those kind of things is really, really common in our retail perspective.
So this is almost like a data aggregation engine that collects all the facts, and then the engine can go back and tie the facts and create like a decision, routing decision that say, okay, if this happened, then there is a more likelihood of this happening.
Exactly, you can easily see the relationships, much easier than the complex queries that you would have to make in, for instance, MySQL. To see all of these relationships, you would have to do a lot of joins, which makes it painful and slow.
Yeah, and I think unlike the regular relational databases where you have to define the relations beforehand, it sounds like in this case you don't have to, you just collect the facts, and then you can run queries that join those facts together.
Exactly, so you can collect all the data and then you can run queries on data and see how it connects. But the relationships themselves, when you connect the data, you may also want to connect the relationships, because otherwise you just have nodes without any relationships, and then you can't make any queries on them. You always have to know which relationship it has to each other.
Is it easy to go back and create like an index on those known facts? To go back and create like an index on the relationship?
Oh, definitely. You can make indexes, and then you see that you need indexes on later on after you collected the data.
Are there any use cases you can think of or types of data where you think this wouldn't be good for?
For instance, I worked for a chemical company with tons of chemical data. And that chemical data was just tabular data, so I had this chemical with this boiling point, this blah blah. And I don't see why you would use a graph database. It's a lot of writes to a database, and all you want is, you don't want any relationships out of it. So any data set where you don't have any relationships, I don't see a reason to use a graph database.
So the browser tool that was used, it was also charting the relationship. Is that like built in to like really draw complex relations also? Or like to what level does it really go about doing that?
Yeah, you can make as complex relationships as you want. But I found when I had a really, really large data set, my browser was actually hanging when I tried to get all the graphs back. So you might want to put a limit, and then it works. But if you try to get millions of nodes inside of the browser, it crashes. But you can easily query the database that way, just not display the graph.
What is the, so is there another view? The other view just shows you the raw data. Does it look like a traditional database, or does it look like JSON?
JSON.
is there a level of complexity of those relationships that where, like, you reach the tipping point where you should go to this relational, to this kind of database versus MySQL? Like, do you need 5 levels deep, or like, what's the point where traditional is no longer good enough?
I guess when you have a lot of join cases and it starts getting slow, you can try experiments with graph databases and see if it's getting quicker. But I can't put a number to it. It also depends on the data set. There's so many figures to it. Thank you.